Hello, welcome to another module of this course, Analog Circuits. We are now in week 3. In the last module, in the past week, we had just started with frequency response, and we had discussed the low frequency response of an op amp and how to find the lower 3 dB frequency in terms of the dominant poles. In this module, we shall be continuing on the same discussion, but for the higher frequency response. So, I would like to just remind you once again what the characteristics were of high and low frequency response. So, there were the general response of an op amp can be written something like this. Now, this is the mid band gain, where the gain is relatively flat, and for both when the frequency decreases as well as increases, we find that the gain decreases. Now, usually this, as I also mentioned in the last module, that this omega L is not always present. Hence, in most cases the response is like this, where only there is an upper 3 dB frequency present. Now, in the past module, we had covered the derivation of this omega L. In this module, we will study how to find out this omega H if the transfer function is given to you. So, the transfer function that we discussed in the last module was of this form. Now, as you can see that when s equal to infinity or tends to infinity, the magnitude of H will be equal to 1, and for when the value of s is less, that is when s equal to 0, depending on the values of omega z's and omega p's, the magnitude of, we can make the magnitude of H of j omega lesser. So, this kind of transfer function is not suitable for high frequency response, because there does not appear to be any dip of the magnitude of H with increase in frequency. But what if I write my transfer function in this form? If you see this transfer function, then what happens now? At s equal to 0, at s equal to j omega equal to 0, magnitude of H of j omega is equal to 1, isn't it? And when s tends to high value, so this is my transfer function. When s equal to j omega tends to infinity, the magnitude of h of j omega becomes equal to 1 upon omega z 1, 1 upon omega z 2, on omega z n upon 1 upon omega p 1, 1 upon omega p 2, 1 upon omega p n. You see that depending on the values of omega z's and the omega p's, we can make h of j omega tending to be lower. Now, if you see fundamentally, if you go back to the two transfer functions once again, so you see that, so this is the for low frequency response and this is for high frequency response. Is there anything fundamentally different between the two? No, see, actually they have the same structure. So then how is it that this is giving, or rather apparently giving, a low frequency response with an omega L clearly defined and omega H not clearly defined, whereas here omega H is clearly defined, but omega L cannot be defined. Why is this difference? The difference arises due to the difference in the values of the omega z's and the omega p's, that is it. Depending on how you design your omega z's and omega p's, you will get a different transfer function, because see, this is also, we can just take omega z1 here and then solve for this equation and we will get a similar transfer function like this, or we can also reduce this transfer function to a form like this. So the difference is just the values of this omega z's and omega p's, that is what makes the difference between high frequency response and a low frequency response. So now let us see how we can obtain an equation or obtain the value of omega h that we had described previously. So omega h once again is given like this. It is the upper 3 dB frequency. Okay. So just like the previous case, if we have a transfer function with just 2 zeros and 2 poles, and then find out the magnitude square of the transfer function. So we will get something like this in that case. Okay. Now at omega equal to omega h, this becomes equal to half, just like the previous case. So in other words, this becomes half at omega equal to omega h, and then solving. So we can simply write this as, instead of, we can substitute omega h here, and then solving for omega h, what we will get is an expression like this, or omega h is nearly equal to Now, the concept of dominant pole for a high frequency case is slightly different than that for the low frequency case. In the low frequency case, we saw that omega p1 should be greater than other poles and zeros. Here, the dominant pole should be lesser than 1/4 the value of the other poles and zeros. That is, if suppose this is omega p1, then all other poles should be at least 4 times away, like this. Now, this is the formula when we have 2 poles and 2 zeros. We can actually generalize it for any number of poles and zeros present in the transfer function. So, the general formula is if this is omega p1 is the dominant pole, then this omega h is nearly equal to omega p1. Okay. So, in other words, when a dominant pole is present, the upper 3 dB frequency is equal to the dominant pole, just like the case for the low frequency response, then the dominant pole itself is the lower 3 dB frequency. Now, taking this a bit further, how to, so we saw our response transfer functions for the case when our response is like this or our response is like this. So, how to obtain the transfer function for the case when our response is like this? So, for that we can simply have our overall transfer function as the product of 2 transfer functions, one taking care of the low frequency response and the other taking care of the high frequency response. So, the final transfer function will be something like this. This whole thing multiplied by okay. So, this is the part caring for the high frequency response. and this is the part taking care of the low frequency response. Of course, final values will depend on how carefully we choose the values of the omega z's and the omega p's. How can we find out the values of these poles, by the way? Suppose you are given a transfer function or you are given a circuit. What is the easy way to find out these poles and these dominant poles? So, one method which is popular is that suppose you have a transfer function given like this, now it can be shown that this B1 is given by the poles omega p's like this. Okay. And this in turn is given like this. Now, here this C I, suppose your circuit consists of a number of capacitors like this. Suppose this is your circuit, then this R I 0 is so for each of these C's, the value of the corresponding R I 0 will be the value of the equivalent. Suppose let us consider this C 2. If you want to find out say R 2 O, then R 2 O is the equivalent resistance across the two terminals of the capacitor with all other capacitors opened. Okay. So, you just open all you open C1 or just remove them C1 and C3, then the equivalent and of course, C2 is also removed. Then the equivalent resistance between these two terminals will be the value of R20. Now, if there is a dominant pole present, now here you can see by the way that this represents the high frequency response, because when S equal to 0, the magnitude of H of j omega is equal to 1. So, here if a dominant pole is present, which is at least 4 times lesser than the other poles and zeros, then we can reduce this. This can be written as 1 upon omega p1, which is equal to 1 upon h. Hence, omega h will be simply equal to 1 upon sigma C I R I 0. Okay. Now, proceeding similarly for the low frequency response also, we can obtain a similar formula. Suppose your transfer function is given like this. Now, you can see that this is the low frequency response, because for S equal to j omega tending to infinity, this magnitude is equal to 1. Now, we can write this E1 is equal to the summation of all the poles, and this E1 is also given by this formula. Okay. where if we go back to this circuit, the CR2S or CRIS, this value. So, here this CRIS, which is the new constant that we found, is the equivalent resistance across any capacitances with all other capacitors sorted out. So, if you want to find out say R2S, then what we do is we short C1 and C3 and then find what is the equivalent resistance. R2S is the equivalent resistance across the terminals of this capacitor C2 with all other capacitors, that is capacitor C1 and C3 shorted. Okay. And then if omega P1 there is a dominant pole present, then that will be at least 4 times larger than other poles and zeros. So, this will be nearly equal to omega P1, which is equal to omega L. Okay. So, this is how we find the lower cutoff frequency from the circuit, and this formula we use for finding out the upper cutoff frequency. So, in this module we covered the high frequency response of an op-amp. We also found out the formula for obtaining the values of the upper cutoff and lower cutoff, upper 3 dB and lower 3 dB frequencies, and how if we are given a circuit, how we can find out based on the resistance and capacitance values. In the next module, we will be covering an example that will illustrate these concepts better. Thank you.